Here's a lecture about Anova. So the motivation for using Anova to compare the means of multiple groups is to avoid making many pairwise comparisons. If you just have two groups, you can use an independent samples t-test to compare the means of those two groups. But once you have more than two, the number of pairwise comparisons goes up with the square of the number of groups, and so it quickly gets out of hand. So what you do instead is you measure how much of the variation that's visible in the whole data set is explained by variation among the means of the different groups. So are the groups separate from each other? And the farther they are from each other, relative to how variable they are within each group, the better your data can be explained by being from multiple groups. So we call this analysis of variance. So let me go over that thing that I just talked about with pictures. So imagine we're talking about the heights of basketball players on different teams. So for each team we find the average. Since those are averages, the central limit theorem says that we expect them to be normally distributed. We might have data from a whole league distributed like this, so each of the different teams. But if we break up the league into conferences, it might look like this, where each individual conference has its own distribution. And you can see that, I'm going to sneeze. Alright, anyway, that's going to be funny when it happens. You know, this gray one, the CES, is sort of spread out. This blue one is more centralized, but they have sort of similar means. And this orange one looks like the teams might, on average, be a little taller. So how do we test that mathematically? We use Anova. So a word about how we set up our data to do this. Old-fashioned approaches sometimes group the data like this because they're grouping it for hand calculation rather than calculating it with a spreadsheet. And so this makes sense for hand because it uses less space. But for a spreadsheet, it's going to think that this is a single observation and that it has three variables that has been observed for each individual variable. Group A, variable group B, and variable group C. These three measurements all in the same individual. So that is no good. We want something like this, where for each observation, we have the group it belongs to and the value that we've measured. So it takes up a little bit more space, but it makes more sense for a friend the spreadsheet. So going back to our hypothetical example, here we have the overall population and the same group, same population, but overall sample, but the same sample displayed as different groups. And what we are testing is the null hypothesis that says that this is just as good an explanation for height as this. So it doesn't give us any extra information about a player in the large 12's height. We say they're in large 12, we just say they're from this overall population. So that's our null hypothesis. But all the groups are being sampled from the same underlying population. So our research hypothesis is that at least one of our groups represents individuals who are sampled from some different population than the others. So that would mean that we expect that sample mean to be different from the other samples, and we would call that, only one of those needs to be different. So we do our Anova. We calculate a couple different variances. We calculate the variance of the whole data set. Then we calculate the variance among the means. So between orange, blue, and gray, there's not much variation between these two, but this one's a little farther away, so that's a variance. And then also the variance within groups. So how spread out are the individual groups? And the cool thing about variances is they add together. So the variance that's explained as the difference among the group means, plus the variance that's explained as the difference within each group, is going to be the total variance that you'd expect to see, regardless of, just by looking at the whole data set as a single sample. So this variance, because there's one observation for each group, the degrees of freedom for that variance is the number of groups minus 1. This variance, the degrees of freedom is the sample size minus the number of groups, because we have to find a mean for each group. And that gives us a total number of degrees of freedom of n minus 1. And n is the sample size. So then the test statistic that we compute is called the F statistic. And that is the variance among divided by the variance within. Since those two sum to the total, that means that this is all the information that there is in the sample. So if most of the variation goes into the part that is explained by differences among means, that means this is going to be bigger when the groups are more spread out, or when the variation within groups is really small. So each of these variances has its own degrees of freedom. So the F distribution has two different parameters that are confusingly both called degrees of freedom. The numerator degrees of freedom and the denominator degrees of freedom. So here's an ugly cartoon that I made showing some different cases. So here we have a low F statistic because all of the different distributions are overlapping, and they're about just as much spread among group means as there is within groups. So this F statistic is probably going to be around 1. Here, we've included the same cartoon bell curves, but I've spread out the means more. So the variation among groups is higher than over here, although the variation within groups is the same. So that means the F statistic is going to be larger because they're more spread out. So there's more variation in this data set than in this data set. And that's one of the reasons why the F statistic is bigger. This data set, on the other hand, has less variation than this one because the centers of each distribution are in the same locations as here, but now there's less variation within each group. And so that means there's going to be a high F statistic because the variance within got small. So you can see the F statistic isn't directly affected by how much variation there is over the whole sample, but it's more how it is broken up between groups, the variation, how far the groups are spaced out, and how variable the groups are within themselves. So you can watch this video on your own. I basically slide these back and forth and show how the F statistic changes. So when we are computing an analysis of variance, the spreadsheet does it for itself. And so before we had that column of data, right, where you had the variable, the groups, and the observations. So in the spreadsheet, you're going to have to enter it and find where a group summary table like this is, and enter in the groups from your data here. So it won't necessarily be A, B, and C. It might be apples, oranges, and bananas, or left, center, right. And it will find the averages. It will find the variation within and the variation among, and add those together. So this is going to be the F table that compactly summarizes our findings. The sum of squares among it has to do with how far apart the groups are. The sum of squares within has to do with how spread out the groups are. And then this total, if you took this total and divided by this degrees of freedom, you would get the sample variance. So then we take this sum of squares divided by the degrees of freedom, we get this is the mean, this is the variance among, or the mean squared among. Those two terms are equivalent. This is the variance within, or the mean squared error within. And this F ratio is this mean square among divided by the mean square within. And then this p-value is the probability of observing an F statistic of 4.9 or larger when you picked a number at random from an F distribution with 2 numerator and 21 denominator degrees of freedom. So when we report the F statistic, when we report the Anova, we report the F statistic, both the numerator and denominator degrees of freedom, and the p-value. And then we report the mean and standard error of each group's values. And if the Anova is significant, you report which groups seem to have different values, and use a bar chart. So it looks something like this. F, that's our stat. The first parameter for our stat distribution is the numerator degrees of freedom, so 2, comma, 137, that's our second. So we can look at that and say, okay, there's 3 groups, because this is going to be the number of groups minus 1, and there's 140 observations, because that's the total sample size minus the number of groups. The F statistic is 7.32. The probability of observing an F statistic that big, given that we were pulling a number at random from this F distribution, is less than 1 in 1,000. So that would be interpreted as that at least one of these groups is bigger than at least one of the others. And so we would say probably this large 12 is being drawn from a different population than these two, just based on the way this graph looks. And that would be how you report the ANOVA.